Hello everybody. Uh, Today's lecture we'll be talking about the operator formulation of quantum mechanics. In this lecture, basically we'll start off with studying what are the postulates of quantum mechanics, which will lead to the need for operators. Then we'll look at water operators. Then we'll we'll study operators for very dynamic variables. Then we'll end with something called commutation of operators. Okay, what is physical significance, and then commutation of operators for different dynamic variables. Now, first we'll recapitulate a bit. Again, we're looking for a correspondence from outcomes as released by it is outcomes, which leads to the concept of something called states of a system. Then, having finished the experiment, we retrieve the outcome in has a probabilistic nature in quantum mechanics. So there we retrieve the values of a particular of outcome in a statistical manner, and these outcomes are called observables of a system. Now, every physical system is formed in terms of certain mathematical objects. So, given a physical concept, we have to map it or have. Now, sometimes this mapping is evident as we have in classical mechanics, but in some cases, like in quantum, is not that intuitive. So, we have something like, sorry, while we have something like laws of mechanics or Maxwell's equation of electromechanics or the Boltzmann equation, give the corresponding behavioral patterns of a classical system behaving on classical mechanics. Similarly, for a quantum system, the corresponding set of rules governing the system is given is have the name what's called postulates of quantum mechanics. Okay, now let's look at the first one. The first postulate states that every physical realizable state of a system described where psi contains all the accessible physical information about system. So, as we seen earlier said, that physical realized states that corresponds to that. Say psi 1 and psi 2 represent two physically realized systems for a given quantum system. Then a linear combination of them is also applicable or a plausible physical state of the system. And a linear combination of all of these possible states is known as a state of a system. Now, the second postulate. The second postulate states that P dV or mod psi square dV, where psi is the wave function, gives the probability of finding the particle at a time t in a given interval dV. Now, this again is a direct consequence of Bohr's interpretation, where he correlated a wave with the physical presence of a particle by relating the amplitude of the wave, both square of the amplitude of the wave, the probability of finding the particle. So, if for a particle to be present in a given volume, the total integral probability in that volume should be equal to 1, or rather, mod psi square represents the probability density of finding the particle in that given volume. Let's look at what constitutes an ideal wave function. Now, in an earlier lecture, we've seen that the Schrodinger equation defines the law which will govern the behavior of the wave function. Now, for a wave function to be applicable to a Schrodinger equation, what property should it have? First, as I said, since for the particle to be present in a system, the sum of the probabilities in that volume should be 1. That's the first criteria. The second is the state function must be single value. What does it mean? Say if it is not single value, that means for a given point of x, there are two values of psi, which implies that two values of psi square. That means a single point of space has two properties. Now that's not possible physical system, right? So Psi has to be single value. The third point is the state function and its derivative must be continuous. Now, this is a property we will use as boundary condition in many potential problems later. In a later lectures we see. Now, what does it physically mean? Say you have a plot of psi versus x here, and this is a point of discontinuity. Now, if you make a derivative here, so say psi 2 and psi 1 are the two values there. So we get psi 2 and psi 1 by delta x, where delta x tends to 0. Now, so you see, since psi 2 is not equal to psi 1, so this leads to a infinite value. In a similar manner, if you plot d psi dx versus x, again the point discontinuity will give a value of infinity for d square psi dx square. Now, we'll see that I cross d psi dx is the momentum of the particle. Similarly, d square psi dx square is proportional to the energy of the particle. So, since energy and momentum, they can't be infinite, so psi and d psi dx, they have to be finite. In other words, there can't be any points of discontinuity. Okay. Now the third postulate. To every observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. For now, forget about the word Hermitian. So an operator is now strictly mathematically speaking, an operator is defined as a we have function fx and operator a. So a operating on fx gives a function psi x. Now, in a special case which we'll be concerned with, special case class of operators, where if the function fx be such that psi x is proportional to fx, that means we can write fx as psi x as a into fx. So, in that case, this a is known as the eigenvalue, a is an operator, and f is known as the eigenfunction. Now, although Postulates mentioned Hermitian operators, it has been seen in later years that in certain cases, non-Hermitian operators have also been found to produce observables, that means physically measured values. Now the fourth postulate. This we've already learned earlier, that the wave function or state function of a system evolves in time according to the time. All the properties of the system, and the operator is a sort of a measuring instrument which allows you to extract the information. Okay. Earlier, as I said, afx equals psi x. Okay, so a is eigenvalue, f is eigenfunction, and a is operator. Now let's look at a real life problem. Say I have a bunch of grapes and I want to measure its weight. Now this is a weighing machine. Now see, the number of grapes here and there here are the same. That means the weighing machine is not in any way affecting the number of grapes here. It's not eating any of them. Okay, so this remains same. This is the value given by the weighing machine. So if you can say that the bunch of grapes is an eigenfunction, the weighing machine is the operator which measures some value of some property of that eigenfunction, and the measured value which I get is the eigenvalue. Now say now can we have operators for everything else or anything in the universe? Say I want to measure your or my intelligence. Can we do that? We cannot. In other words, we can say there is no operator for intelligence. Now say this constants function fx equal to into ikx minus omega t. So this basically represents a wave traveling in the positive x direction. Now using operator minus I cross dtx. When we apply it on fx, we get this minus I. So the function, since this is the fx part, this operator operating on fx gives back my all in fx along with the value h cross k. This is my eigenvalue. Now we know h cross k is what? Momentum, right? That means this is an operator which operating on a wave function gives me the wave momentum of this particle or this system. Now we'll look at an operators for different dynamic variables. First of all, let's say position vector A. I showed in the earlier lecture. We start with a wave function a to I k x minus omega t, differentiate with respect to x. So the I a minus I h cross del del x is the operator which operating on psi gives me the momentum. Similarly, this is for the excitation. Similarly, if you work for y direction, it will give minus I h cross del del y and z minus I h cross del del z. In a similar manner, for three-dimensional system, we'll get IPX plus JPY by KPZ, or we can get minus I h cross del operator. Now, potential energy. This again is intuitive. V into psi. The potential, as we saw earlier, is minus. We differentiate with respect to x. Okay, so we get P psi into del psi del x. Multiply both sides by minus. And if you combine all three for a three-dimensional system, we have ikx plus jky vector z, or minus h cross square by 2m del square. Now total energy. Now we look at the time part. Differentiate the wave function with respect to time. So my one way of treating this is another way. Now here we know kinetic energy is minus h square by 2m del square Lx square, and potential is V. So the total energy is Ke plus P, that means P square by 2m plus V, or minus h square by 2m del square Lx square plus V into psi, right? Now this is known as the Hamiltonian or the total energy. We know angular momentum is L equal to R cross P, right? So R is the position vector and P is the momentum. Now we apply the cross product here. Okay. Now if you see I X is, this part is Lx, this Ly, and this is Lz. Now this is one way of writing. Another way is, if you put it, see, we know I cross del del z was what, Pz. So we can also write it as Ypz minus Zpy. Similarly for the other cases. Now sometimes we get a problem that what are the eigenvalues of Lz? Now till now we've restricted ourselves to Cartesian coordinate systems. Now for this problem, just assume that you knew the value of Lz in the polar coordinate system. Okay? So Lz is minus h cross del del psi. So if you apply Lz phi equal to lambda psi, so lambda is the value of Lz here. So it becomes a del del psi minus h del psi, or del psi by lambda, and that in a just proceed as normal integration way, we get psi equal to minus I h cross lambda psi. Now say since we are treating with a spherical system, angular system, that means if we compound for one circle, the value should be the same, right? That means it should be single valued for rotation by 2 pi. That means psi phi it should be equal to psi phi plus 2 pi. Now if you put it in place of this eigenfunction here, we get 2 cross lambda psi equal to cross lambda psi plus 2 pi. So that implies that e to the cross lambda 2 pi, that this factor should be equal to 1. Now we know that e to I 2 pi k is equal to 1. This is normal property of complex numbers, right? So if we compare these two values, it shows that I cross lambda 2 pi should be equal to I cross 2 pi n, or where n is an integer, which implies that lambda equal to plus minus n. That means the eigenvalues must have integer values, or you can say the eigenvalues of the angular momentum vector form a discrete spectrum. Now, the next topic we'll cover is commutation of operators. Now, say we have two operators A and B. The commutation operator method, it means, is something like this with the square bracket C equal to A comma B. It implies that we do this multiplication A into B minus B into A. Now see, say we have an operator A, this AI matrix, and this B. This AB and this BA. Now if you go, that means if you do A comma B, that is computation of A and B, we get something like 2AB. That means it is not equal to 0. Now the two operators set to commute if AB minus ABA equal to, that means AB equal to B. Okay. Now what does it physically mean? This mathematics is fine. Say I'm looking at a system where I want to measure the height. I first measure the height and then measure the weight. In the other case, I first measure the weight and then measure the height. Now in H and they just say W. I want to measure the time taken to run 100 meters and the amount of water a person can drink. Now, if I say ask a boy to first run for 100 meters, then ask him to drink water, naturally he'll drink a lot of water. But if I ask him to drink water to his fill and then ask him to run, naturally the time here and the time here won't be the same. Similarly, the amount of water taken here and here won't be same, right? So here the order of measurement alters the values, right? So this class of measurements can be called as non-commutative, where the order of measurement is affecting the results. So if you look at a physical perspective, it means that if A and B commute, then they have a set of non-trivial common items, like simultaneous measurement of observables corresponding to the operators. Otherwise, there would be a trade-off in accuracy. So naturally, the pairs linked by Heisenberg's principle, like XP or since they are linked by that H cross factor, the Einstein principle forbids them from simultaneous accurate measurements. Right? So these canonical conjugate quantities, they can never commute. Now we look at a few rules governing these comparators, which we may call look at a commutation for a few dynamic variables. Then we look at commutative algebra. So first say we'll look at a commutation between x and p. So replace p by its operator. So p psi s minus px. So first we do it px into psi x. That is what we do it, and then x into pi xp into we'll do it. Px into psi x minus sorry x into p into psi x minus px into psi. So replace p by its operator in both cases. Now here, since psi x is outside, so this operator doesn't affect a del x. But here, since the del x comes first and then x is inside, so here you do a differentiation by parts, right? So we get I square del psi I x plus x del psi x. Now expand it, and we get something like I equals psi. So p into psi and x into psi, the two values are not same, we get something like IH cross. That means they do not commute. As we said earlier, since x and y are it by Heisenberg's uncertain principle. We die. Similarly, for if you move p with py, y with py, will get IH cross. Similarly with z and pz. If we look at commutation of the angular momentum with position vector. So Lx minus into x minus x into x. Now replace Lx by its operator value, okay, minus x into again this one. Okay. Altered you can write, as I said, Lx into x minus x into x into psi. Okay, so replace this with psi, x into psi, and here this comes later. The x comes first and then. Now, if we expand, we look at this definition and expand, we'll see that it comes to 0. These factors cancel. Similarly, Ly with y and Lz with z will give 0. That means Lx and x commute, or they can be on a system. These two operators can be applied simultaneously to give acute values. Now, if say we look at xl, earlier we looked at Lx with x. Now say we look at Lx with y. X and Lx commute, but Lx and y, X with z will give IH cross y. In a similar manner, that means we sum up. We will see Ly with y is 0, Ly with z is IH cross z, Ly with x is I minus IH cross z. Similarly, Lz with y, Lz with z will be 0, but Lz with y is minus IH cross x, Lz with x is IH cross y. Now, we get computation between the angular momentum themselves. Say Lx and Ly. That means Lx Ly minus Ly Lx. So we'll have just apply. Okay, here we will short form that y into pz. So just expand. Okay. So this Lx Ly and this is Ly Lx. Again expand this function. If we subtract, we get something like this. Y pz pz z. Right. Now we know that what? We know that pz z. Okay. If we go back a bit. See. ZPZ is what? Lx commute to give sort of a cyclic rule. So if you commute these two, you will get this one with an IH cross. Similarly, if you commute these two, you will get this one with an. Now, we look at a few general rules governing commutators. Now, this is intuitive that A into B should be equal to minus BA naturally. Now, say we have something like A commuting with B plus C. So this follows a sort of a distributive law. So it becomes A comma B plus A comma C. Similarly, A plus B dot C. Sorry, this is A plus B comma C. Here again AC. These two are similar. Now say we have A and B dot C. So this follows something like A dot A B with the C outside. Similarly, so see this B C, one C remains outside, and the other case is this first one B remains on the left side. Similarly, for A dot B with C, AC B remains, and then A is first of all BC. Now we will see a few applications of these rules. Where do we need it? Now say we have done for x and px, right? Now say I am asked to do a computation of x square in px. Now from rule 5, we know a dot b comma c is a comma c b plus a b comma c. So this x cross can be broken up into x dot x. Say one is both are a and b are both at x. So this comes to x, xpx and again xpx x. Now we already done xpx as IH cross. So it becomes 2IH cross x. Similarly, if you say equal to do x to the n and px inclusive x square. So say x cube, say, so x cube becomes x square px, again x square outside. Now we already done x square px as I h cross, so put it there. So in a similar manner, if you proceed by induction, we can say that for x to the power n, if we have, it becomes n into I h cross x to the power n minus 1. Here we've similarly for x and px square. So it's x px outside. Again here, just put the value of I h cross here, it gives 2 I h cross px. Similarly, in a manner by induction, x and px to the n will give n I h cross px n. Here it's given commutation between Hamiltonian and the momentum operator. Put the values here. So again, so it becomes a plus b comma c, that form. So break up a, c and b, c. Again, px can broken into px into px px. Right? Now we know px with px should be equal to 0, right? So this becomes 0. So we have to live with px into px. The constant operation of a function psi. So hpx psi becomes vpx minus pxv into psi. Put these values. So it gives hpx equal to minus ih cos hx. Thus we say that for a particle with a constant potential or a free particle, the momentum and the Hamilton operator, they commute. Now this next one, L square with Lx, Ly and z. Again L square, you can break it by Lx square plus Ly square plus L square. That means a plus b plus c sort of like. So a is a, c, b, c, and again c, c. We know again Lx square, Lx can go come into Lx into Lx. So it becomes Lx outside, right? So this again 0. So if we put it that way, if we put it in a similar manner, we will see that the entire thing comes to 0. Similarly, L square Ly and L square Lz will also be equal to 0. Okay. Now we started with something in the third point. We said something called a Hermitian operator. So what is a Hermitian operator? A Hermitian operator is one which follows this rule: a psi complex is equal to conjugate of psi squared a psi. Now the significance of Hermitian operator comes from this theorem, that the to have an observable in a system, we apply a Hermitian operator and you extract the real value observable. Look at the proof of this. Say let psi be an eigenfunction of A with eigenvalue capital A. You put it here. Then we do a complex conjugate. So A psi in place of A psi, just put this one. Okay. Bring it outside. Now by Hermitian, this is equal to, following this rule, is psi straight psi, right? So since A is a real number, we get what? Psi straight psi. That means since these two are equal, basically what we get is A equal to A star. So that can only happen for a real function. That means the eigenvalue A has to be real for Hermitian. Okay. I'll end with this one words. As someone said, quantum mechanics is nothing but linear algebra.